Watch as this F-106 pulses its ailerons, and the rudder automatically responds to achieve a coordinated turn. The underlying linear simulation about trim reveals further details. Observe the aileron pulse in magenta for roll, followed by the rudder in cyan for coordination. The aileron pulse serves to roll the aircraft, while the rudder acts automatically to eliminate side slip, that is beta, keeping it near zero and hence the turn coordinated. This was achieved with a lateral flight control system. It involved a yaw damping inner loop and a side slip regulation outer loop, known as a beta-beta dot controller. When tuned, these control loops provide automatic rudder action in response to roll input through the aileron, where the aileron input up top acts directly on the aircraft roll dynamics. This control system coordinates the turn so that no rudder input from the pilot is needed. Let's represent the closed-loop system as a single block called the turn-coordinated aircraft. In this lesson, our goal is to link lateral stick motion in the cockpit to a signal that goes into the aileron servo, going into the turn-coordinated aircraft to produce a desired turn. This is achieved with a yaw-orientation control system. Now, this controller has two objectives. First, we must achieve the commanded turn rate. And second, we must regulate residual roll rate that is induced from the aileron action. This small roll rate is observed in the drifting roll angle after the aileron pulse of our previous simulation. So to achieve our first objective, first suppose there's a transducer that relates stick motion to a desired yaw rate or turn rate command. We'll feed back yaw rate to produce ultimately a turn rate error and then use integral control to drive that error to zero and therefore track turn rate commands. Second, we feed back roll rate with its own proportional gain through the integrator to regulate roll rate and therefore eliminate the roll angle drift. Finally, there's the pilot rudder pedal input. It's shown for completeness but remains zero throughout this lesson. So architecture is one thing, but tuning is another. To fully develop our controller, we will tune in the time domain with a root locus and the simulation of the closed-loop aircraft dynamics. We'll also explore the frequency domain with multivariable Nyquist stability, singular value stability margins, and the multivariable Bode's theorem. And finally, we go in detail on the development of the state space models and the controller behind this analysis. The end result is with the single action of lateral stick motion, the aircraft automatically banks to turn without skidding or slipping, automatically achieving an efficient coordinated turn. So let's continue with the root locus. The goal of the root locus analysis is to observe the change in the closed loop response as the controller gains are varied. From these changes, we tune the controller for the best stability and transient properties. To compute the locus, we form the closed-loop system in state space, then compute the eigenvalues of the closed-loop system, and plot the series of points or locus of eigenvalues to observe their paths. To build our complete closed-loop system, first start with the beta-beta dot controller. Then add the additional feedback loops of the yaw-orientation control system. Now we've already tuned the beta-beta dot controller in the previous lesson. We'll keep this tuning here and tune the outer two loops in the yaw-orientation controller. Typically in control tuning, we work from the inside out. So the first root locus will investigate the yaw rate feedback loop without the roll regulation active. That is, we set Kp equal to 0 in the outermost loop. This leaves only the single integrator gain Kr that is free to vary. Physically, the drifting of the roll angle is not regulated, so we may expect slow divergence in roll angle as the aircraft roll rate converges to a constant value through the stable roll mode. In the root locus, the blue circles are the open loop eigenvalues corresponding to the three lateral rigid body modes, the Dutch roll, the spiral, and the roll mode. The actuator poles are at -10. Now, varying Kr from 0 to 5, observe the locus. Do you have any concerns with the closed loop paths? We should be concerned. There's a complex pair at the origin that immediately branches off into the right half plane. This is a closed loop, unstable system where instability is increasing as the controller puts more effort into the aileron to achieve the commanded turn rate. Physically, what's happening here? Let's try to explain this by examining the branches of the root locus. The open loop rigid body modes are easily identified from their physical characteristics. There's the spiral mode, a slightly unstable mode responsible for the spiral dive if left unchecked. There's the Dutch roll mode, a lightly damped complex pair. And the stable roll mode, governing the decay of roll rate. Then further left with timescale separation, the rudder and the aileron actuator poles, both at -10. Note, there are more closed-loop eigenvalues in white than open-loop eigenvalues in blue, due to the presence of two integrators and a washout filter in the controller. It can be tricky to trace closed-loop eigenvalues to their processes. This is because, in the limit of low control effort, while closed-loop eigenvalues approach open-loop eigenvalues, here we have an existing tuned beta dot inner loop controller. However, we can also use eigenvectors because they point to the states that correspond to the eigenvalues. Applying this approach, there are two complex pairs that together pertain to the Dutch roll mode, the rudder servo, and one integrator. There's the roll mode, the washout filter, and near the origin, the spiral mode and the yaw-rate integrator form the unstable complex pair. There must be something destabilizing about the interaction between the spiral mode and that integrator. Clearly, one source of instability is the additional 90 degrees of phase lag that the integrator creates, apparently eliminating the phase margin that the system had. We observe the instability in linear simulation. Here's a plot of the states and control inputs for the integrator gain of 0.45 and Kp equal to 0. The aileron and rudder on the bottom row attempt to compensate for the instability, oscillating, but nevertheless, the states diverge. From what first appears to be a coordinated turn, evolves into swaying of the aircraft in the roll and yaw directions. Look at the control surface action, scaled up here for visibility. The rudder and elevon unsuccessfully execute the turn in the presence of the unstable spiral integrator pair. To stabilize the roll axis, we now explore the roll rate regulator loop. There is a root locus for each value of Kp, where Kir is varied as before. Starting with Kp equals 0 for reference, what do you observe as Kp is increased? The unstable complex pair becomes stable for a range of Kir, and that stability increases as Kp increases. But with almost any tuned parameter in feedback control, there's always a trade-off. What trade-off did you observe here? Look at the roll mode. For positive Kp, the roll subsidence mode becomes less stable as KIR increases. Therefore, the aircraft roll rate will persist for longer, but it will fully regulate to zero through the integral action, and thereby eliminate the drift in the roll angle. Even though the roll mode slows down moving right, it's not necessarily the dominant eigenvalue. That is the washout filter. A washout filter is a high-pass filter. Here, it allows low-frequency yaw rate associated with turning objectives through the control system, but it attenuates higher-frequency Dutch roll oscillation. Its pole is just right of the roll mode and dominates the closed-loop response with a time constant of 3.7 seconds. Now, we have stabilized the spiral integrator pair, but once stable, these eigenvalues must have enough damping to avoid unwanted oscillation in the closed-loop response. The chosen design point is a compromise between roll mode and washout filter time constant and the minimum closed-loop damping, which was achieved in that spiral integrator pair of 0.51. This corresponds to the gains 0.45 and 0.25. This concludes the root locus analysis. Let's now move on to simulation of this tuned control system. We now test the closed-loop control system with a 2 degree per second turn rate step command input. We expect to observe tracking of the step input with a time constant of about 4 seconds based on the dominant eigenvalue of the closed-loop system. After running the simulation in continuous time, the closed-loop states and control inputs are plotted. First, we observe asymptotic command tracking of the yaw-rate command input with a time constant of about 4 seconds as expected. Note the undershoot. It indicates this is a non-minimum phase system with a right half plane 0. This turn rate was achieved through a 28 degree bank angle. Notably, there's no drift in the bank angle as before. So a single integrator in the yaw-orientation outer loops, those 2 loops, successfully did 2 jobs: yaw rate tracking and roll rate regulation. And this is all accomplished while side slip is maintained near 0 with the highly effective beta dot control system. Thus, the turn is nearly perfectly coordinated. To achieve this coordinated turn, the controller commands both aileron and rudder action. The aileron's primary role is to bank the aircraft to achieve the commanded turn rate. The rudder's primary role is to coordinate that turn, that is, regulate side slip and dampen the Dutch roll mode. Now, the simulation visualized with the F-106 aircraft. To achieve the turn, there are brief transients in the control surface deflection. Then the aircraft achieves a steady state turn as desired. The pilot would struggle to compete with the rate that this tuned automatic control system achieved a coordinated turn. However, with this system, the pilot can have excellent turn performance while focusing on other tasks. In addition to the time domain response tested through simulation, we can also learn much about the robustness of this system with frequency domain analysis. We'll start with the multivariable Nyquist stability criterion. Here is our closed-loop architecture. We can clearly distinguish between the plant and the dynamic controller. Notice the signal dimensions. The plant receives 2 control inputs and generates 4 distinct measurement outputs. Because these multiple channels interact simultaneously, we classify this as a multi-input, multi-output, or MIMO system. Recall the multivariable Nyquist stability criterion. It states that the closed-loop system is stable if the number of encirclements of the critical point is equal to minus the number of open-loop poles in the right-half plane. 0 is the critical point. N is the number of encirclements of the critical point. Gamma n is the D-shaped Nyquist contour with large radius in the right-half plane. P is the number of open-loop poles in the Nyquist contour, and LU is the loop gain transfer function at the plant input. We obtain the loop gain transfer function by breaking the loop at the plant input and forming the transfer function minus U out over U in. Here, our loop gain will be a 2x2 transfer function given the two control inputs. To compute the Nyquist diagram, we must evaluate the determinant of the return difference transfer function over the Nyquist contour, where the return difference is I plus LU. It can be shown that this determinant is equal to the ratio of the open loop characteristic polynomial to the closed loop characteristic polynomial. The characteristic polynomials are determined for the open loop system as the determinant of Si minus A, and for the closed loop system as shown. Thus, the determinant of the return difference can be computed as shown. Of all the ways I could have determined this transfer function, you may ask why I showed it this way. The reason is that working in Octave, I found this transfer function approach was least prone to numerical error using this formula. Now, providing this transfer function to the function nyclog, available on MathWorks Exchange, this full Nyquist diagram is obtained. It is necessarily a closed contour that is supposed to be axisymmetric about the real axis. The asymmetry in the crescent shape, I suspect, is due to some numerical error in evaluating the transfer function or the resolution of the points defining the D-shaped Nyquist contour. This was not further investigated, but otherwise the diagram is symmetric. This is a logarithmic radial plot that more easily allows inspection of the encirclements. Note the units of decibels marked at -120 near the origin, where the origin is also the critical point at -infinity decibels, and the tick marks increase to 60 decibels as shown. The 0 decibel line is also shown, which converts to a magnitude of 1. The low frequency part of the plot has the greatest radius away from the critical point. The direct current, or DC gain, is when 0 frequency is input. It's a real number where the diagram intersects the real axis on the left. Let's follow the blue line. It's generated through evaluating the determinant of the return difference over gamma n with positive frequency, from low to high frequency, where the transfer function ultimately approaches 1 on the real axis. As the determinant of the return difference is evaluated for negative frequencies, the dashed yellow line is produced. It traces the mirror image of the blue line from high frequency to the DC gain closing the Nyquist diagram contour. Carefully counting the number of encirclements, we determine 1 net clockwise encirclement of the critical point. Therefore, n equals -1. There is also 1 right half plane open loop pole. Therefore, P equals 1. We conclude this system then is closed loop stable because by Nyquist's criterion, n equals -p for stability. We'd like to proceed from here with robustness analysis. But unfortunately, in contrast to the single input system, distance of the multivariable Nyquist diagram to the critical point is not a measure of robustness. However, singular values do provide a measure of nearness to instability. Using singular values, the stability robustness test states that for the multiplicative disturbance matrix between the plant and the controller shown, call it delta, the closed-loop system is stable if the max singular value of delta inverse minus identity is less than the min singular value of the return difference over frequency. This turns out to be a conservative stability test because the block delta can be unstructured. That is, a full complex block where that disturbance could occur in a worst case direction. This test is also sufficient to prove stability, but if the test fails, the system could still be stable. Since disturbances are often structured, for example, diagonal, a more accurate bound could be obtained with mu analysis or the structured singular value, but we don't go into this method here. The bound for the uncertainty on the right-hand side is the minimum singular value of the return difference transfer function. Using properties of singular values, this is equivalent to the minimum of 1 over the maximum singular value of the sensitivity transfer function. Evaluating this for our tuned control system, we obtain this plot where the minimum of 0.42 is easily identified. Therefore, we can guarantee closed-loop stability provided the uncertainty magnitude remains below 0.42. Let's now test this stability bound with a structured uncertainty. This means that the delta block can be represented as a simultaneous disturbance in the aileron and rudder channels, where each disturbance is modeled as k times e to the j theta, where k is a gain disturbance and theta is a phase disturbance, which by Euler's formula shows it's just a complex number that's in that channel. Let's do an initial test that increases the effectiveness of the aileron by 30% and decreases the effectiveness of the rudder by 25%. The matrix becomes 1.3 and 0.75 on the diagonal. Is this system guaranteed closed-loop stable? Let's check. Here's the left-hand side of the stability robustness test. Its maximum singular value is 0.33. Since 0.33 is less than 0.42, we can conclude the system is closed-loop stable. Stability is great, but has this changed the performance of the system? After all, we've significantly changed the control effectiveness. Looking at the closed-loop simulation, we observe small, almost negligible change to the closed-loop response. Nyquist encirclements confirm the stability of this system, showing no change to diagram encirclements. All right, let's try to break our closed-loop system. Let's hit the aileron with a 60% reduction and the rudder with a 50% reduction in effectiveness. The left-hand side becomes 1.5 in the stability robustness test. This is more than 3 times the stability bound. Therefore, the system is now not guaranteed to be closed-loop stable. But it still could be. What do you think? Stable or unstable? Let's look at the simulation. We observe oscillation, an indication of nearness to instability, but nevertheless, the signals converge and track. Wow! And the Nyquist encirclements confirm it. All right, let's try again. Same reduction in control effectiveness, but a 40 and 30 degree phase increase in the aileron and rudder channels, respectively. We are now 4 times over the threshold. Is it stable? That is the question. The closed loop response is not stable. Numerical issues prevented correct Nyquist analysis, but we can revert to a closed loop plot of the eigenvalues and show the single unstable pole. These tests are manually probing the margins of the system. How much can we tolerate in gain and phase before going unstable? Of course, a trial and error brute force approach to quantifying margins is inefficient, but stability margins based on singular values do exist. They can be derived from the stability robustness test, and for the multiplicative disturbance, we arrive at a formula for both positive and negative margins in gain and phase. They're computed with the minimum singular value of the return difference, or the inverse of the maximum singular value of the sensitivity. We previously determined this upper bound for the stability robustness test. Now substituting that bound 0.42 into the margin formulas, we arrive at guaranteed margins of -3 to 4.7 decibels for gain and plus or minus 24.2 degrees for phase. I know what you're thinking. These numbers look low. Usually for a scalar system, we demand at least 6 decibels of gain and 30 degrees of phase margin, but remember this context. This is the guaranteed floor. It assumes the universe is conspiring to hit us with a full matrix of disturbances in the absolute worst case direction simultaneously. Because this test guards against such an unlikely perfect storm, it's naturally conservative. In reality, margins in any individual channel are much likely higher. And since we're close to these standard thresholds, even under the worst case assumption, and our manual tests look pretty good, we can proceed with some confidence. Now, hidden within our tune control system is a distribution of that sensitivity transfer function across the frequency spectrum. Is our tuning truly balanced, or are we pushing up sensitivity in certain ranges of frequency? To understand this, the answer lies in Bode's integral theorem. Gunther Stein famously called Bode's integral theorem the conservation law of control theory. It tells us that the total area under the sensitivity curve is fixed. It's equal to pi times the sum of the unstable open loop eigenvalues. And here's the thing for MIMO systems. The integrand isn't just a simple scalar sensitivity. It's the natural log of the determinant of the sensitivity matrix. Mathematically, the determinant is the product of the singular values. So you can think of this as the total volume of sensitivity. We can squeeze the shape, but we do not change the volume. This means that if we want to reduce sensitivity in one channel over some frequency range, it must cause amplification elsewhere. And that elsewhere could be a different frequency, or more dangerously, a completely different channel. That's the waterbed effect. The more unstable our open loop system, the larger total volume of that sensitivity we have to manage. And here's the practical implication. Suppose we aggressively tune the aileron channel for perfect tracking. Because of this conservation law, we may have inadvertently amplified sensitivity in the rudder channel, making the aircraft vulnerable to yaw disturbances without even realizing it. To observe this, we look at the maximum singular value plot. You can see how our tuning has squeezed the sensitivity into the worst case direction, creating significant peaks of nearly 8 dB, well above a typical 3 decibel threshold. But when we view it from the perspective of Bode's integral, we're looking at the total volume of the sensitivity, and we see much less peaking. This tells us two things. The cost of our open loop instability is low because the unstable spiral mode is very slow. And while the perfect storm direction causes concerning amplification, the other directions have minimal sensitivity. The controller has effectively put sensitivity into a disturbance direction that we hope won't be excited, while maintaining the required sensitivity total volume. If the plane were more unstable, say the pole were at 1 instead of 0.004, the math would demand an increase in the sensitivity volume, and we would be forced to accept more sensitivity elsewhere just to stabilize the system. We can think of our sensitivity as a balloon. When we tune the controller for performance, we're effectively squeezing the balloon in the middle to reduce the air in the channels that we care about. But we have to respect the conservation of volume. By squeezing the middle, we have inadvertently forced that balloon to bulge out, creating an oblong shape. This elongation represents sensitivity accumulating in the worst case maximum singular value direction. So will our system actually fail? Well, Murphy's Law says we must prepare for that perfect storm, where disturbances hit exactly along that axis. But in the real world, the system might never actually experience the full brunt of this worst case peak. As an appendix to this lesson, let's briefly discuss how the state space systems were developed. Recall our full lateral control system. Breaking out all the control loops, we observe the full detail of the controller. Our analysis of this system involves constructing state space models for the plant and the controller, where the plant receives the control input U, outputs the measurement Y, and the controller receives the two inputs Y and R and outputs U. Note the feedback channels Y and the command input channels R are separate inputs into the LTI dynamic controller. Let's first look at the development of the plant state space system. From the full 6 degree of freedom model, we have trim and linearization to obtain LTI dynamics to capture the rigid body modal response of the lateral system due to aileron and rudder deflection inputs. This is in a standard LTI model form. Also part of the plant are the control servo actuator models, here represented as first order systems. Taking the inverse Laplace transform, we get the two-state LTI system that outputs achieved control actuation deflection. Each channel has an eigenvalue of -10, giving a time constant of 100 milliseconds. This also reduces to just another standard LTI system. Now to form the full plant, we substitute the output of the actuator model into the input of the rigid body dynamic model. This gives another LTI system that correctly couples these as two processes in series. Note this is simply not concatenating or stacking these systems together. The couple through the series connection is apparent with the term BP times CA in the 2-1 spot of the A matrix. With the plant, now let's move on to the dynamic controller development. The way to approach this is starting with the innermost loop, working out the state space system, moving on to the next outer loop, working out its state space system, connecting the two state space systems, and then finally working on the most two outer loops into a state space system to connect with the inner loops. These connections in state space will involve substitutions of outputs into inputs, and in some cases, simply stacking state space systems together. The key is to try to keep the math consistent with the diagram. Ultimately, we get the 4-state dynamic control system. This is built upon the dynamic controller of the previous beta dot control, where new inputs and gains and states are highlighted as shown. Ultimately, we have the generalized dynamic controller. And so we have the two primary parts of our control system. The fact that many control system architectures can be put into these forms enable us to develop and use common tools to form things like loop gain transfer functions, return difference, sensitivity, closed loop systems, all conveniently for performance and robustness analysis, as we showed in this lesson. Our efforts that have sought to tune for performance and verify robustness result in a flight control system that allows the pilot to move the stick laterally and achieve a desired turn rate. The flight control system eliminates the need for manual adjustment to the rudders so that the pilot can focus on the mission. In this lesson, we sought turn coordination of an aircraft through a pilot lateral stick input that would command a desired turn rate, where pilot rudder input for turn coordination was not necessary. We proposed the two-loop yaw-orientation controller for the aileron channel and applied this controller to the closed-loop turn-coordinated aircraft. We explored the tuning of the closed-loop system with the root locus, ultimately arriving at a tuned system and then simulating and visualizing the aircraft response to a 2 degree per second turn command. We then showed how the multivariable Nyquist stability criterion could be applied, and our results were consistent with our tuned system eigenvalues. We sought to quantify the robustness of our system with the stability robustness test, and we showed how it was quite conservative due to its assumption of an unstructured uncertainty. Singular value stability margins were computed and were shown to be below standard thresholds for single input systems, but were deemed reasonable given their conservatism. We then investigated the control system with Bode's integral, interpreting our tuned results in the context of a sensitivity volume that had been squeezed in worst-case directions. Finally, we briefly showed the state-space models used in this analysis and described how they could be developed from the block diagram. We found that the yaw-orientation control system was effective at achieving the desired turn rate that could be easily connected to lateral stick motion. The root locus was an effective means of tuning the controller. As a MIMO system, everything was coupled and required singular value analysis. Bode's integral was a reality check against worst-case sensitivity that the stability margins were based on. A less conservative analysis would involve structured uncertainties, and these are arguably more realistic. Future topics to this lesson include performance weighting functions that can force desired controller behavior. H-infinity synthesis can squeeze the controller to behave like the weighting functions intend. Uncertainties arguably enter in a structured manner. Therefore, for more accurate robustness analysis, the structured singular value mu could be applied. And mu synthesis with the decay iteration creates controllers that are iteratively optimized for the structured uncertainties, potentially more specific and relevant to our aircraft. Access this lesson and more at learngnc.com. If you're a Patreon subscriber, thank you very much. Your support keeps these lessons coming. If you're interested in supporting the channel, obtaining the codes used to create this lessons and all of my previous lessons, special tutorials, lesson previews, and more, then check out Learn Guidance and Control on Patreon. That's all for now. Until next time.